So someone says it's not audible. I got a message from Imanshi. So is it so? Please send some chat or something in case you don't hear me still. Maybe I try. Okay, so now is it better? Okay. So I hope you can all hear me.
Yes, sir.
Okay. Fine. So yesterday I just briefly touched upon the turbulent flows. I mentioned that flows at very large Reynolds numbers, a very typical situation in astrophysics. You expect the flow to be turbulent, in which case basically the energy cascades down to much smaller length scale where it is dissipated, uh, yielding a universal Kolmogorov k to the minus 5/3 type spectrum. You will hear more about this from Professor Drupaditya Mitra in lectures on turbulence. So I will not spend much time on that. But the essential equation for that is basically given by this equation. So this is the equation that governs all those interesting phenomena. And as you will also hear that this term, though very, very small, as you can argue that at Reynolds numbers of 10 to 13 or 10 to 20 or even 10 to 30, this term must be so much negligible compared to this that it can be very safely ignored, but it does play a very crucial role at some stage of the cascade of the process. Okay. Anyway, I also showed you some pictures and was asking the inviscid case, which means nu equals 0. And if you were to stick nu equals 0 in this formula, you would find the infinite Reynolds number. So it sounds as if the flow must be infinitely turbulent or something, right? And so what do you expect for the behavior? And that you please continue to think. If it was a regular class, I would have had discussion and chats with you. But please also try to think right now about what do you think about the air in your room? Is the air in your room turbulent enough? And you can freely write your such short responses in the chat, that I can somewhat monitor. Even one or two people write. That's also fine. That do you think that the air in your room is turbulent, or how do you guess, or how do you estimate that? So one easy way, and that is also an exercise for now. Again, it's a topic that you learn from turbulence. I'll just hint a little bit, given that all of this is anyway coming from this type of equation. Now, if you look carefully, so I hear that it is turbulent when fan is on. It's actually not necessarily, it's not true actually. It's even otherwise turbulent enough. Okay. Yes, fan increases perhaps a little bit the Reynolds number, makes it maybe more turbulent, but even otherwise, and one, I can suggest an experiment or just make a very small quick calculation, and then you'll get to know immediately. What is the dimension of this quantity viscosity? It's actually, I'm not writing too much here, but we can more like chat. And if you are making any notes, so please note that this quantity viscosity has the dimension of length square divided by time. That is the dimension of this quantity nu, viscosity. Okay. Now, if you take a typical length scale of your room or a typical object in your room, say 2 meter, 3 meter. So you just take a number for 2 meter, 3 meter. Find out what is the viscosity of air in the room at 30 degree centigrade and stuff. Just Google this and try to determine. I immediately don't recall. Work out that time scale that it would take for a motion. After all, what is this thing doing? that if you have a motion, which is a velocity in the medium, this term will basically lead to the dissipation of that motion, right? It's like a friction term. Then you ask, over what time scale? So if I started with velocity v over a length scale L, what is the typical time that it will take for it to dissipate away the energy? So you can very dimensionally, you can construct an argument that this nu is length square by time. So time is, how will you say? Length square divided by nu, right? Dimensionally, you can write time. So you just please write like time. Maybe I can even try annotate here. So in case, just to maybe, I don't know where it is. I thought I remote control. Oh, wait. Anyway, never mind. I think now how do I get rid of that? Never mind. I was just trying to annotate to draw something here, but I think it's tough. I'm surprised. I thought it was very easy here. Anyway, never mind. So in case you are writing, so you can write down what I'm trying with my mouse, if you can see, that a typical time scale to dissipate away the energy and stuff. So suppose you moved your hand and then there was some associated motion of fluid around your hand, which you couldn't see, the air you don't see, but suppose you were to imagine, of course, when somebody is fanning something, you can feel the wind or breeze on your face, so that's how you can feel it. And so suppose there is a fan in your room, typical length scale, you know, time you can determine by length square, just put 2 meters square, it will become 4 meters square, divided by nu, viscosity of the medium, you say the SI unit, and then work out the time that it will take for that motion to dissipate. And what do you think, if some of you can send me a chat, what do you think the time that it takes to dissipate the energy in a viscous manner? By viscous manner, you are simply saying that the medium is laminar, it's not turbulent, and therefore the time scales are governed by this term. Only then you will be in a low Reynolds number regime, in which case the time scales and dynamics is entirely determined by this term, and therefore we are focusing on this term. So if you were to take this term and imagine that the air in your room is not turbulent, suppose, then you would have taken this number. So I can give you the answer. So when, in your experience, you might have seen that when you switch on the fan, you feel the wind immediately, and when you switch off, the circulation immediately stops. Right? Circulation in the room immediately stops because you stop feeling the wind, the breeze on your face. You stop feeling it. And why so? After all, any circulation that you drove through the fan, it must have dissipated over a time scale of L square by nu, and that if you work out for the air in your room, you'll find that the number is in days. It should have taken few days, about I think 11 days or something. It takes 11 days to dissipate the energy or motion through viscosity, microscopic viscosity. So it's good to feel sometimes what these numbers tell you. It will tell you that simply the air circulation should stop on the order of 11 days or 10 days. But what is your experience? Similar thing will apply to your friend walks next to you and has put on a perfume. These companies will be bankrupt if there was no turbulence in air. And the reason is, as soon as the person walks by, you want to recognize that person with that particular perfume, and that's how these companies run, right? So, and how does it happen? That as soon as the person walks by, you can smell the perfume. But why? After all, any perfume molecule or anything that is, it's like you are breathing out the perfume from your clothes, and that's that mixed with the breeze and reaches your friend's nose, and you can work out again the time scale that it takes to reach for the perfume molecules to reach from friend A to friend B. Again, that time scale for a non-turbulent medium, for a laminar medium, will be governed by again this term. Again, you can work out what is the viscosity. Microscopic viscosity is the property of the medium, will not depend on whether there is a cyclone outside or not. It is the property of the medium, the temperature and stuff like that. In fact, I'll come to what it depends on. And then you simply determine this number. And then again, a person walked by, molecular diffusion should have given you an answer on the order of days. But now that particular person wanted to be identified with that perfume, right? But then it took days for the effect to reach you. Maybe you even were not anymore standing there to witness the perfume, right? So the same thing again is that then clearly this is not driven by this term. So this is one test, a very easy test, that air in your room is very much turbulent. So that's what it is determined by that. So what is this doing? It's another thing. So the quite empirically you can see that the effect, at least one prominent effect of turbulence, is to enhance the diffusion such that the time scales are much shorter, right? The time that it was taking, say, 11 days is now seconds by this term. It's an orders of magnitude difference in time scales, right? So these are almost like a magical terms. Okay. So now it has become seconds. So that means the diffusion, this is causing a diffusion from a molecular motions. This will give you some turbulent viscosity type of quantity, which will sit in a more mean field type of sense, which I will actually, I did not cover, I think, the mean field in the last year's lectures. But this year, I am taking one extra lecture. So maybe on Monday, I will sketch how a mean field modeling is done. And how do you see that from this term, a new like term emerges out and sits with a Laplacian. It's almost like a magic that you do something with this equation. Basically, you average it and smooth it and stuff. And a turbulent viscosity like term emerges, and you can write that as nu plus nu of T, which is turbulent viscosity. And that turbulent viscosity is orders of magnitude larger than the nu. So if I have a term which is A plus B bracket Laplacian of a quantity, but B is much larger than A, so clearly A is not playing any role whatsoever, right? And that's why you can still just drop this nu, but the dissipative effect might emerge from just this term alone. Okay? You can forget about gravity for that matter to understand just this very basic. The stratification is not playing any extra or major role here. Just forget about it. So just think of this very simple looking equation. It's very notoriously hard equation. This plus this equal this plus this. That's your usual Navier-Stokes equation. A source of all fun and misery. Yeah. So that's all I would say for turbulence. So please note that the microscopic diffusion is not playing major role or is not controlling the dynamics, not even in your room. Forget about the astrophysics, where it, of course, doesn't play any role for some smooth large-scale dynamics. So everything basically is governed by that, including that perfume that you just witnessed from your friend. Okay. So now I quickly go to plasma part, only the macroscopic part, and I will not spend too much time again on this. I'll simply sketch my motivation to why I'm going to plasma physics, and so that by motivating you to think about the magnetic fields in the universe, what you can say cosmic magnetic fields. That is the main theme that I want to convey. The origin of cosmic magnetism. What is the origin of magnetic fields in the universe? You can also ask the question, right, that if the turbulent diffusion is so large, it will be the same for also the magnetic field, which I will show later. But you can imagine that if the turbulent diffusion is so large, that means the quantities are dissipated away, right? I mean, the circulation stops. That means this quantity V becomes zero very quickly. The question is, you still see the wind, you still see the magnetic field in the universe. How come? It should have all been dissipated by the diffusion coming out of this type of nonlinear term. So you should immediately ask question that if dissipation is so much larger, what is it that is maintaining the wind? What is it that is maintaining the magnetic field in the universe? Why do you observe any magnetic field in the universe? It should have all been dissipated away from nonlinear terms or nonlinear interactions or turbulent interactions. It should have been dissipated away. That is the, seems like some empirical evidence. And that's when the some other interesting science starts, is how do you generate these? What is the generative mechanism and what is the dissipative mechanism? Right now, I can simply say that both effects can emerge from this single term here. This same term, which you can write somewhat differently and write in terms of the Reynolds stress. If you take the Reynolds average of this equation, you'll find something like Reynolds stresses coming out. They can have both non-dissipative and dissipative processes, both coming out from this. And therefore, if you reach a fine balance, the inductive or the generative mechanisms can overcome the dissipation and therefore lead to various interesting things. Right? So the questions are multifold, and so it's very mysterious. So that's why I'm simply making certain statements and just trying to force you to think that it's not as simple the story as I'm trying to draw, that the turbulent viscosity is killing the motion and all that perfume diffusion and all that. If that was so only, then still all the wind and breeze and everything should have just stopped. What is it that is driving it? More interesting or interesting enough is also to think about the magnetic field. So that's why I will not spend too much time on plasma, the details of plasma physics. I suggest you go to some books, like say even the book by Anna Brai-Chaudhary or this Boyd and Sanderson, or any book of your choice. Every book will cover very similar standard thing. So there is no much mystery. Why are we interested? Why am I interested in plasma part? I'm not interested in say the details of the electrons and ions as such. I'm mostly interested in the collective behavior of the plasma, or the what you call the fluid-like description of plasma, which you call a single fluid or magnetohydrodynamics. So it's a subject of magnetohydrodynamics in which you don't differentiate or you don't identify individual charged particles. Just like I was, while defining the fluid, I was mentioning that individual molecules don't matter anymore. What matters for you, or what is the lowest resolved scale for you, is the fluid particle, which comprises of many, many molecules which you don't know about. Similarly, for the MHD, smallest entity is just like a fluid particle. It has many, many charged particles and stuff, but you don't know the finer details. So it's a collective behavior or collective response of a very many charged particles that comes out. And what that does to the medium is of interest to understand various interesting things. So for example, it's good to just observe quite an interesting thing, that the magnetic fields, there's some impressions taken from Google. You can over a range of scales, and I've stopped at the sun, or maybe not. No, I have not. I've stopped at galaxy maybe. You can go to much larger scales. You can start from your lab, from your room, where you can see the magnetic fields over a scale of say 1 meter. If you go to the Earth scale, you find a magnetic field on the order of 10,000 kilometers. So it's a very large scale magnetic field also for the Earth. You go to the sun. Sun has a diameter of 700 megameter. 700 megameter. So diameter is 1,400 megameter. So roughly you can say that it's a 1,000 megameter body. 1,000 megameter body. So, right? Over all that entire sun, there is an evidence of large and large scale magnetic field. It goes from large magnetic activity. It's still a very active area of research. That how does the sun has very magnetically active phase. Sometimes when you see the sun these are the magnetograms of the sun, where the white and the black patches are the vertical or the radial magnetic fields coming out from the white and going towards inside. That is the black part. So it's a bipolar magnetic field, which are also known as the sunspots or active regions, which are very strong magnetic fields. Yeah, you can zoom in and you find that one sunspot, you can see this is the approximate size of the Earth. It can be much larger than the size of the Earth. Right? So one spot is like, say, sometimes 30 megameter, 40 megameter. Right? This is what Earth is. What 10 megameter. Right? 10,000. So you take these three with kilometers. So it's a 10 megameter object. A typical spot can be, say, 20 megameter, 30 megameter, much larger than the Earth. A lot of very powerful extreme events happen from these sunspots, these coronal mass ejections or the solar winds, solar flares, prominences. So these are very interesting, powerful events in which there is a lot of mass loss from the sun. So it can even be very harmful for the life on the Earth if one is not lucky enough. We have been very lucky. So these are very powerful events that are powered by this tiny for the sun. It's a tiny still for the sun features that are the dark spots on the surface of the sun. Why are these dark? You might have heard already from the solar physics course. Because when you look at the sun, these little yellow patch, when you observe more carefully, you find that these are very grainy things. That's actually convection, surface convection, photospheric convection, in which there is a plasma motion coming up and down, basically to transport heat from the interior of the sun to the energy that we see from the sun. That heat is generated by the nuclear reactions in the core of the sun. At some point in the outer layers of the sun, it cannot be transported by conduction or radiation, and outer layer of the sun becomes convectively unstable, and therefore the heat is coming from convection. When there is a strong magnetic field, that basically inhibits the convective motion. Therefore, the heat transport from here is not that efficient. So these are cooler regions, relatively cooler regions. That's why look darker on the surface of the sun. So very interesting thing in itself. Without magnetic field also, you can see that the convection is a very interesting process. But we are marching towards the magnetic field. So it's very interesting, quite an active area of research, that how come the magnetic activity has a very interesting 11-year cycle for the sun. It goes from high activity, and then there are phases when there is no sunspot or active region, then comes back, and then the cycle repeats. And the sun has like this 11-year cycle from high to low. Okay, so it's very, very interesting. But again, thing to note from this is that the very large scale magnetic fields are also observed also on the sun, on the system scale. Whichever is the system, you find the magnetic fields on the system scale. You must already start wondering that why are we not talking about the electric field and only the magnetic field? Yeah? After all, you must be reading electromagnetic field and stuff, and one can convert the one from the other. It's not that straightforward. So I will try to convey some details, but right now it's good to just note that we are interested in the magnetic fields in the universe. We want to understand the origin of these magnetic fields. We want to understand what is it that is maintaining these magnetic fields? After all, any magnetic field that is there, it must be dissipated away. Why should it emerge? Once it has dissipated, why should it come back? What is driving this? Yeah. Lifetime of the sun is very old, and if you work out the decay time scale, even taking into account the turbulent decay time scale of any field is actually very short. Just like we argued for the air circulation in the room, also for the sun or galaxy. These are very beautiful aurora. So when you travel towards the North Pole, this happens quite routinely there. That the charged particles from the sun, primarily coming say from these active regions, but there is a solar wind all the time. So charged particles coming from the sun, they interact with the upper layers of our atmosphere. Yeah, and because these charged particles can come from anywhere, but because the magnetic field is dipolar for the Earth, all of these charged particles are coupled and they basically interact mostly in these polar regions here, right? Here and here, polar regions. And when these charged particles are hitting the upper layers of atmosphere, they produce various beautiful colors. And it's an amazing scene. If you travel to say Finland or Norway, Sweden, very up north, you will quite easily observe that this is what is happening. These are just bombarding charged particles in the atmosphere, causing excitations in oxygen, nitrogen molecules, leading to various optical colors. Sometimes there is even pink here. Mostly it is green. And it just travels like anything. It's a pattern very beautiful. But again, this is all done or due to the magnetic fields. So magnetic fields you observe everywhere. Now, if you go to the sun and earth, there is an interplanetary magnetic field is pervading all the intermediate space. It's permeating everywhere. So wherever you observe in space, you can't see them, just like air in your room, but it is there. The magnetic field is basically everywhere. So that is now the size which is 1 astronomical units. Now you go to the entire galaxy. By now you must have seen very many pretty pictures of various systems, galaxies, AGNs, jets, black holes, whatnot. So you can now go back and again look at those and wonder that do magnetic fields exist in all of those? The answer is yes, it exists in all of those. And not only that it exists with some property which is rather remarkable. Remarkable is that if you try to think harder and harder, you must wonder, how come there is a magnetic field which is as large, the scale of magnetic field, that means it varies very, very smoothly, the scale over which the magnetic field exists. See, these are smooth field lines. These are the drawn contours over the magnetic field contours. So this is like as large as the size of the system itself, like 10 kiloparsec scale magnetic field. It's an enormously large magnetic field, right? Question is, how do you produce these magnetic field? There is no battery. I mean, here, there was a battery of this size, and therefore you produce a magnetic field on this side. On a galaxy, where is the battery? How do you produce a magnetic field which is of this size? Even if you think that magnetic field must be produced by, say, some motions in galaxies or sun is occurring in a very tiny, small length scales, right? The largest scales of motion, say in a disk galaxy, like a spiral galaxy, could be what? The disk scale height, the thickness of the disk. If you were to look at this edge on, the thickness is roughly what? In the inner parts is about 500 parsecs, say half a kiloparsec. That is somewhat like the scale over which, say, the supernovae will drive the energy, and that is roughly the scale at which the energy is existing, the kinetic energies. Yeah? Typical kinetic scale of kinetic energy from which you may hope that you can drive the magnetic field, that is still much, much smaller than the scale of the magnetic field. Question is, how do you not, so there are two questions. How do you generate this magnetic field? And how do you generate this at this larger length scale? How does it go from this small length scale to large length scale? Or how do you understand this very large scale magnetic fields? It's a very interesting problem. Yeah. And it's still quite an active area of research. So, before you go to the magnetic field generation in astrophysics, let's step back and start for just like for the fluid from the particles. But again, we will quickly abandon the idea of particles and come to some collective behavior and write down some fluid-like equations. But right now, let's start again. Just like for the fluid, we had some condition, right? The two particles should not have come so close that their de Broglie wavelengths were overlapping and stuff. So they must be dilute gases, but still there must be very many, and the mean free path must have been very small, so that a typical fluid particle continues to retain its identity, and the molecular identification is no more needed. Right? So that was a fluid. All of that is still applicable here. There is an additional constraint here. Okay. And that additional constraint will come in terms of, say, Debye length and plasma frequency. That, for the astrophysics, I'll be actually rather quick because I don't want to invest too much time on this. I think I've already spoken half an hour just on these somewhat pretty pictures. But it's interesting. You can go to somewhat larger scales, say clusters of galaxies, and you will still find, on a megaparsec scale, you will find the magnetic field. Even more curious is to observe magnetic fields in the voids. You know, the cosmic web you might have seen by now. If not, then you look up. There's an entire cosmic web in cosmology, and there are cosmic voids you might have heard. Even in those voids, people have observed magnetic fields on a megaparsec scale, megaparsec scale. So it's really rather remarkable. How do you produce magnetic fields on that kind of enormous length scales? So it's a very non-trivial thing, but nevertheless very interesting. And one is still trying to understand more and more about it. But yeah, the story starts from particles, of course, that if you want to generate a magnetic field, the first thing that comes to mind is that, well, we should have currents. And for currents, the thing comes to mind that we should have charged particles. Charged particles in motion drive currents, and those currents can lead to the magnetic field. So charge is in motion, isn't it? And astrophysics is full of charges, charged particles, and there is enough reason to believe that the motions are driven by, say, some even external factors. Say two galaxies are merging and colliding and troubling each other and causing various motions. Individual baryons or the particles may be in charged state, in a plasma state, and naturally they are in motion. So it's easy enough to imagine that there may be associated magnetic fields. It's not just that. So please try to read, if you are interested, read as much as possible. I will only sketch that plasma you define as a quasi-neutral mixture of ions and electrons that exhibit collective behavior. So how do you guarantee a collective behavior? It's just a term. Collective behavior is that you are again not looking at a single charged particle. You are looking at a collective behavior of a very many charged particle whenever you are observing something, say, at a distance. The thing is, you might have heard about ISSAA ionization equation, that at a given temperature, and say there is an ion number density Ni, that heating up the plasma, heating up the medium, say you start with a neutral medium, so that's a neutral number density. You start with a medium which is neutral, and you start heating up the gas, you will see that there will be more and more electrons coming out, and more ions will be produced. This is the corresponding ionization potential of that species. You can have a multiple species here. So it's easy enough to imagine that heating the gas will lead to ionization in the medium. And as soon as you have a very little ionization, you don't have to have a fully ionized case, even very little ion, 1%, 2% ionization, degree of ionization, still enough to basically put these charges in motion, and then you have a current and associated magnetic field. Right? I'm still not talking about the electric field. And why so? So let's wait a bit more. So we are focusing on the space plasma, which is nearly fully ionized. But even otherwise, even a little bit of ionization will be still okay for our story here. Try to draw how does this curve look. Try to see what is the behavior of this function. Read more about the ionization equation. It's very, very remarkable equation. You can actually come up, and when there is an ion, there is also electrons. Yeah, ions and electrons are basically bunching together. So you can at least naively expect that if I take a large enough volume, there will be as many ions as many electrons. Thus, the total charge of that volume, it's not that difficult to expect that the total charge of a volume may be zero. Plus and minus from ions and electrons, they may balance out each other. So if you were to take an electric field due to such collective bunched ions and electrons, the electric field at a much larger distance may be zero, right? Isn't it? You draw your, again, Gaussian surface, electric field at a given distance r, at which you have drawn a Gaussian surface, must be determined by the charge that is enclosed by that Gaussian surface. Now that I just said that you may be having a quasi-neutral mixture of ions and electrons, though the enclosed charge Q is actually zero, and therefore there is no electric field at the distance. But what about the magnetic field? Yeah. So keep thinking in these directions, and I will only be hinting things here and there, and then it calls more for the reading. So Debye length, and you can read further about Debye. It's a measure of a shielding distance, which is proportional to the temperature and inversely proportional to the electron number density. It's very interesting that it is inversely proportional to electron number density. Okay. That basically means that if I have gone for a distance of Debye length, the influence of the electric field for of a charged particle, say I put a minus here, suppose I draw a minus here, minus will attract enough plus here around the plus, right? And now you are working out a distance over which you travel so that the electric field due to the minus charge placed at the center has been screened out totally by the plus around it. Okay. So if I take a minus charge here, there will be plus around it. And if I go a distance, say, over a couple of Debye length, the plus and minus, I will see the effect of both plus and minus, and will lose the information in an electrostatic sense, lose the information that there is any charge, because the electric field has been totally screened out by these more positive ions around that negative charge, right? So it's a shielding distance. So while in principle, the electric field due to a charged particle goes all the way up to infinity, right? Electric field, how do you write? 1 by 4 pi epsilon 0 Q by R square. So if you have a charge Q, the electric field can be felt all the way up to the infinity. But I'm just suggesting a situation in which there is enough shielding by the plus and minus, and electric field is actually shielded over a distance of Debye length. So if you are at a much larger distance, you don't see any electric field. Okay. What you essentially see is a collective behavior of plus and minus. That's what is meant by a plasma. In some sense, is even defined by something which exhibits a collective behavior. If it doesn't exhibit a collective behavior, you don't call it a plasma, in fact. At least in many textbooks, you don't call it plasma. It's a very interesting quantity to define a plasma parameter. In some textbooks, they define it inverse. 1 by so-called ND here is defined as a plasma parameter. It doesn't matter. It's just a measure of a number of particles or number of particles is say the electron number density. It's a number of particles in the Debye volume. It's just some measure of number of particles in the Debye volume, which gives you a handle that how many particles are actually exhibiting the collective behavior. Typically for a plasma, you expect that this must be very, very large, because if that is not the case, then you are actually still sensitive to individual charge particles, which is not what you want. You want effective shielding, effective screening. It's a matter of what time scales and what length scales you are involved. Right? You can work out the Debye length. It can be a very, very tiny scale, but you are interested on a kiloparsec scale. So you may not be interested in what is happening at, say, a nanometer or centimeter or a millimeter or even a meter. What happens over a scale of 1 meter may not be of any interest to you if you are making a simulation or observing a galaxy over a 10 kiloparsec, when your resolution itself is less than a kiloparsec or around a kiloparsec or maybe 1 parsec. So if your resolution is 1 parsec, which is already what? 10 to the 4 orders of magnitude is smaller than the 10 kiloparsec. It's already very many large range of scales involved. 10 to 10 kiloparsec, and then you are looking at 1 parsec. These numbers may be meter, centimeter. So you are not very sensitive to that. So you are not necessarily interested even to look at individual particles. But it's a good thing to have a sense of what is this number in a medium of your interest, given a temperature. You can work that out given these numbers. Interestingly, you note that this Debye parameter defined this way is actually goes as inversely to the NE lambda d cube, but lambda d cube you can work out from here is 3 by 2 it will give. So you'll get something like T to the 3/2 divided by NE to the 1/2. That's how it goes, right? So if you go to a low density medium, it's somewhat non-intuitive, but you can think about it. If you go to a lower density will mean that the lambda d or the Debye length is larger. What does it mean? That if the charge density, not charge density, the number density of charge is smaller, that means say low density plasma, the shielding is less effective. That means the lambda d grows, and that means you have to cover a larger and larger length scale to have a more collective behavior. But look at here, the plasma parameter also grows. That means the number of particles will grow very enormously as you go to lower and lower NE. Right? So in a sense that the collective behavior will still emerge. There is a very interesting quantity called plasma frequency. So you can work out that 1 over frequency is some kind of a time scale. So I'll just quickly wrap it up that by and large one is interested over distances L that are much larger than the Debye length and over time scales which are much larger than the inverse plasma frequency. That means slow dynamics and smooth dynamics. That is required for you to go towards a fluid-like behavior, what you call a fluid picture of plasma. We are only interested in a single fluid for this set of lectures, single fluid description of plasma. So it will be treated as a single fluid. When you define a plasma particle, you are not identifying ions or electrons. You define you assign one velocity, temperature, etc., like a single fluid to that this thing. The only thing is that while the charges can screen themselves out, like plus and minus can screen themselves out, they are still not bound to each other. They are not like in the molecule or an atom. They are still free particles. It's just that you have taken a small volume in which there are as many free charge plus particles, as many positive ions as there are negative ions. But they can move. And as they move, while maintaining the charge neutrality, you can just imagine a wire here, or you can just imagine a medium here. Say wherever you want. Just take a medium here, small little volume, very small parcel here. There is no net charge in the medium. But plus can move here, minus can move there, and driving a current. So current will exist, and that's why the magnetic field will also exist. But there is no electric field outside. Already this puts a constraint that this is a slow dynamics. So it's a non-relativistic limit. So I will not derive in more detail, but please read that the MHD description, so-called magnetohydrodynamic description, is a non-relativistic limit of the full plasma. So in a particle picture, the motion of individual charged particles are studied under the influence of externally applied electromagnetic fields. So it's just like you put a electromagnetic field, electric field, a magnetic field, and you see how the particle evolves and moves, what you might have heard as a plasma orbit theory. That's a very different picture, as even more complicated actually. In a fluid picture, if induced fields are significant, which is the case that induced fields are like the charged particles in motion, they will produce fields, right? And those are very important. Orbit approach is perhaps not very suitable to study the dynamics. Typical length scale and time scales of interest are that the time scales of interest are much larger than the inverse plasma and the length scale much larger than the Debye length. Then charge separation can be ignored. So there is no charge separation. Charges are bunching together and only a fluid-like description becomes possible. So that's what we will focus. That's what I meant by macroscopic description. But still it's harder, but very important to think about the microscopic dissipation. What is leading to the microscopic dissipation? Ultimately, dissipation is very, very critical for all kinds of phenomena. So I think I went very slow, and maybe I should speed up a little bit. Anyway, so electrical conductivity. So you know Ohm's law, right? So let me motivate it somewhat differently. So when you write the Ohm's law, that means if there is an electric current, electric field, and there are charges, the current is proportional to the electric field. And you must have read about the Ohm's law. And the proportionality constant is the conductivity of the medium. It's a property of the medium, just like the viscosity. Okay. So it's a property of the medium, conductivity. You can estimate it based on the electron-ion collisions. Yeah. And it turns out that it's independent of charge density. And as you can guess, perhaps, that or perhaps not so easily guess, conductivity is proportional to the positive power of the temperature. You might want to think, just like the viscosity. So I'll wrap it up, viscosity also here itself. The viscosity also, viscosity is a resistance, and this is inverse of a resistance. Viscosity goes with the positive power of T. Reason is that larger temperature induce more collision and therefore more dissipation, isn't it? So why is that not the case for conductivity? The simple reason is that at larger temperature, for conductivity, you need first of all the ions and electrons. So again, go back to ISSAA ionization equation here. So only at higher temperature you will have enough ions and electrons to drive the electric field, and therefore the conductivity actually becomes larger and larger at large temperature. You define microscopic resistivity, which is defined as C square in CGS unit by 4 pi sigma. Basically, you can write it's like 1 over sigma. It goes as T to the minus 3/2. So the distance behaves opposite to the viscosity. Both are basically leading to dissipation. This is leading to dissipation of momentum. This is leading to the dissipation of magnetic field, or currents. Currents here. Currents you can relate with magnetic fields, right? Curl of B is J and stuff. Maxwell's equation. So this is leading to the dissipation of current, but it goes inversely proportional to the temperature. Very interesting, right? So think more about it. I will come very quickly to the basics of magnetohydrodynamics. So having now defined that in what situations you can imagine the quasi-neutral plasma in which the charged particles are not separated, yet they can drive currents. As I said, the charges are free to move, and as they move, they can drive currents. You write down the whole Maxwell's equation in full glory. And you know this evolution of magnetic and electric fields, and these are the divergences given. Right? What is our goal? What are we trying to achieve from this ultimately? Because we are interested, as I wrote, on the magnetic fields in the universe, cosmic magnetic field, we want to have a dynamical equation of magnetic field. That is the goal. To write down or to derive an equation which governs the evolution of magnetic field. That means del B by del T type equation. Just like we had an equation here, del V by del T. Right? We need a similar looking equation for del magnetic field by del T. Okay? So that is the goal. Under the approximation, there is a plasma, collective behavior, single species, single fluid, MHD, non-relativistic, all that approximation has gone in. Then you derive something like, from here, you can now write a more generalized Ohm's law. Actually, you can write very general Ohm's law, which has a Hall effect, ambipolar diffusion. So you can keep adding terms. But in a fixed frame of reference, if there is a plasma in motion with velocity v, the current J, electrical current J, again the proportionality constant is sigma, which is conductivity, electrical conductivity, with resistivity defined as c square by 4 pi sigma, is instead of sigma E, which was a plasma at rest, but if there is a plasma in motion, you have another term, E plus V cross P by C. Read more if you are interested. Then this is Ohm's law. And you note also that the sigma can be very, very large quantity. Sigma can be very large quantity. So if I take this equation, J is this, and I try to write down this equation here and replace this J by this. Right? J is replaced by this in this equation. You get something like that. Replace sigma by eta and work out this term. This is what? This is a displacement current term, right? So in the non-relativistic limit, you can pretty much imagine that the displacement current can be ignored. And the reason for that is that the changes in the electric field are not noticed. Because the prefactor here, eta by c square, let's just look at the number here. That's known as the Faraday time scale. There are many ways to think about it, but let's look at it here. Tau f, if you work out the Faraday time scale, so-called, eta by c square, which is the term that is multiplying this, you are interested in some slow time scale, right? Because at least time scales that are larger than the inverse plasma frequency. What is this number that it multiplies? Because the conductivity of the medium is very large for ionized plasma, it goes as 10 to the minus 14 of T4, which is temperature in units of 10 to the 4 Kelvin, very typical of, say, galaxy. So this is of order 1 here. So the time scale is 10 to the minus 14 seconds. Right? We are interested in times of what? Mega year, giga year. Right? Mega year, giga year. These are the time scales that interest us in astrophysics. And something multiplying this term has 10 to the minus 14 seconds. So this term, no matter what is this, you are multiplying that because this is very, very large here. So this term can be actually very safely ignored. Other way to think about is that if I have plus here, if I have minus here, charge separation, you can work out the conductivity continuity equation for charge, right? You know that del rho by del T is equal to minus divergence of J, this J, yeah? And use this equation and determine an equation for del rho by del T. You'll find again that the rho, the charge density, decays with a Faraday time scale, eta by c square, charge separation. So plus and minus, if you had here, they will have a locally an electric field, and electric field will be shorted out by the high conductivity of the medium. Conductivity is very, very large. So the conductivity will short out the electric field between the two, plus and minus, because the charges can be separated. Magnetic field does not have any monopole, so you can't short them out, right? So that is a major difference between the electric and magnetic fields. magnetic field, there is no magnetic monopole, so that you cannot short out. But electric field you can short out, like plus and minus will move towards each other, and electric field vanishes, right? So that's what one means by saying shorted out, by having large conductivity. If the medium had no conductivity, they will not be shorted out. But plasma is highly conducting by definition. And that's kind of time scales involved. So what did you get? Is that this term is gone. Electric field you could write in terms of curl B, V cross B by C. More rigorous derivation, please look up some textbook. I will somewhat rush and use this E for this evolution equation. Yeah? Del B by del T is equal to this Faraday's law. So what do you get? Del B by del T is equal to curl of V cross B minus eta. So without, in the ideal limit, for ideal plasma, you know that resistance can be ignored. Or let's first write down, this is known as the induction equation, by the way. It's the most important equation that you will hear in astrophysical magnetic fields. This is the equation. So I just wanted to give you a feel for two most important equations of the MHD. One is this induction equation. Suppose eta is uniform, so curl can operate on minus curl B is actually positive eta Laplacian B. Divergence B term will be 0 because of divergence B being 0. So curl acting on curl B will give you two terms, only one will survive. And you can write for a medium with homogeneous eta. If it is non-homogeneous, then you have another term which is gradient of eta. Right? So please note that there will be a gradient eta type term here also. Gradient eta cross curl B, like that. But suppose you have a homogeneous eta, you take it out and you have Laplacian B. But if I have an ideal plasma or ideal MHD, you ignore any dissipative effect. So you forget about this. So now look at this equation. This you derived rigorously here, right? From starting from the Maxwell's equation, appealing to the Ohm's law, throwing out the term that is negligibly small, you have now derived an induction equation which will give you the evolution of magnetic field. How does the magnetic field evolve? Do you find this similar to something that we studied yesterday? So this is an identical equation. This is a V, is again the velocity assigned to a plasma particle, not to any individual charged particle or individual molecules. It's a velocity assigned to an individual plasma particle. This equation you saw earlier, which was this equation, vorticity equation. That's why we spend so much time on vorticity and circularity. It's a very important concept, very mysterious concept also. If you're not very careful, you may be confused forever, like many people are. So please think and read as much as possible about the vorticity. It's very, very mysteriously difficult. As you saw in some cases like that, free vortex, that it is not, that is irrotational, is not such an obvious thing from just the look of it, right? But it is. So that's why we spend so much time on vorticity. And quite many things will be directly applicable. For example, the theorem like this, Kelvin circulation theorem, is directly applicable also in the magnetic field. In the ideal limit, we'll find exactly similar thing. Instead of V dot dr or d gamma here, what will happen? You'll get something like B dot dA. This form was perhaps more useful here. You can define some quantity like, instead of omega, omega is replaced by B. So B dot NDS, that becomes a conserved quantity. That means flux of magnetic field through a surface remains conserved at all times, or it does not change in time in the ideal MHD. A consequence which is very powerful. Very, very powerful consequence. All this thin vortex tube and that omega, as you stretch the vortex tube, the strength of the vorticity increases with this length, is directly applicable to the magnetic field. So the magnetic field also, as you stretch a magnetic field tube, that will simply increase with it. That's one very easy way to make the stronger and stronger magnetic field. Just take the tube and just stretch it. Okay. As simple as that. And because the equations are very same, so, but also note that there is a very contrasting difference, that Here, omega is curl of V, so it's highly nonlinear here. And that is not the case with B. B is not curl of V. So that equation remains linear, whereas this not. Okay. So there are very interesting similarities and very important differences to note. So I think I did not go too much today, but anyway, I hope it was still useful. And maybe I should stop at just the induction equation. This is your induction equation, which will govern the evolution of magnetic field. I want to, or if you have time, you please read about, take the similar eta that is taken here and work out what is the dissipation time scale of magnetic field for a galaxy. Suppose a galaxy was born with some magnetic field, say 1 microgauss. Work out how much time does it take for it to dissipate away. If you use this eta, just like your viscosity of the air, you will find that this number will give you a dissipation time scale to be larger than the age of the universe. That means the magnetic field should survive. But the point is, this term, although it looks linear and not directly nonlinear, it's still a product between the two terms. Product is, in some sense, as bad as nonlinearity. So you can, for a very practical reason, you can say it is nonlinear. So in a different sense, which I'll come to later, or tomorrow, or on Monday. This will give you additional turbulent diffusion or turbulent resistivity, which will again, just like nu plus nu t, you will have eta plus eta t. Eta t will again speed up the process. That means it will enhance the diffusion or dissipation. And then you will find that the magnetic field, any system, that sun, earth, or galaxy, if it was born with a magnetic field, it would have decayed all its magnetic field within a very short time, compared to its lifetime. But we observe the magnetic field nevertheless. So how and why? So this is called an induction equation because it's an inductive term. It's an inductive term, and this is a dissipative term. In the inductive term, there is also a source of diffusion term. Okay. So I will stop here and maybe take up. I wanted to go to the mean field theory, so maybe tomorrow I'll do something else. Fine, but yeah. So the two most important questions I want to highlight was this equation, induction equation, and this momentum equation here for incompressible fluid. This is for incompressible fluid already. Okay. So thanks very much, and see you on Monday.